Hello and welcome to this video for Chemistry 30. In this video, we're going to continue looking at naming organic molecules. Today, we're going to be focusing on alkenes, cycloalkenes, and alkynes. My last video looked at the other first two compounds, alkanes and cycloalkanes. So here's just a brief overview of the generic formula for them, some examples of how they are named, and some other parts of naming that are important when it comes to identifying the number of carbons in your parent group and how to number the carbons in the parent group. Okay, so going into talking about what is an alkene. First of all, the generic formula for an alkene is hydrogens are double the number of carbons and not plus 2 like the alkanes were. It's just double the number of carbons. So for example, C5H10, C20H40. Now this is the same formula as a cycloalkane. So what that means is if you have a cycloalkane, it can be an isomer to an alkene when they have the same carbons because they will also have the same number of hydrogens. Okay? They contain one or more double bonds, but we're going to focus when they have only one double bond. They are considered unsaturated. Remember, the alkanes were saturated because they had all single bonds. When you have carbon-to-carbon double or triple bonds, that is unsaturated. Okay? They can be a continuous chain, a branch chain, or a ring structure like before, which we would call cycloalkenes, which we'll also look at today. Some of their properties, they are still nonpolar in water. So if you just have, for example, the simplest alkene, which is called ethene, it is trigonoplanar around each carbon. Remember, my lines going to nothing are really going to hydrogens. I just omit drawing them. But they are symmetrical in shape as long as the terminal atoms are all hydrogens, which they all will be in this section. They're nonpolar, so they have only London dispersion forces, making them non-soluble in water. Their boiling point is actually a little bit lower than their corresponding alkane. So ethane, which is C2H6, as opposed to ethene, which is C2H4, I have 2 less hydrogens, so 2 less electrons. Less electrons makes your London dispersion forces weaker. If those are weaker, your boiling point is going to be a little bit lower than something that has more electrons. Okay? They are, however, going to be more reactive because, again, of that double bond. The double bond means there's 4 electrons being shared in that spot. That makes more repulsion, making the bond less stable. Now, there is a diagnostic test that you need to be aware of as to identifying if you have an alkane or an alkene, for example. The way it works is by adding a colored indicator. So this is my colored indicator bromine, which is like an amber color. And then this is another indicator, potassium permanganate, which is a purple color. I'm going to add them to 2 test tubes that start colorless. Both of the test tubes are starting colorless for both of these tests. Okay? When I add the indicator into the 2 test tubes, and then you let it sit for a couple of minutes, if it remains the color of the indicator, that means it is not reacting with the indicator. If it turns to the color of the indicator, it is not reacting. So if something is not reacting, that means it's stable or it is the alkane. However, what is happening with the other sample? It is going back to its original color. It's using up the colored substance, okay? The colored substance is being used up in the reaction. So if it goes back to its original color, that means this is the alkene, the one going back to its original color. So it's changing from the color of the indicator back to its original colorless if that's how it started. Okay? So that's how you can identify whether it's reacting or not. If it goes back to its color, it's reacting, and the one that reacts is the more reactive one again, which is the alkene. And we'll get into these actual type of reactions that they go through later in the units. Okay? Now, what are some uses of them? Plastic, steroids, welding torches like acetylene. Those are different gases that get used, some plastics, PVC for example, and steroids. It is important to know the uses as well as naming and their properties. So when it comes to naming, you're going to give them a name, the same prefixes we use with the alkanes, but they're going to have an ENE ending instead of an ANE ending. Okay? You're also going to number it so that the double bond gets the lowest number. The double bond takes priority. It needs the lowest number. Now you're also going to give a number between the prefix and the suffix if you have more than 3 carbons in your parent chain. Okay? Only if you have more than 3 carbons. Because when you have 2 carbons and 3 carbons, there's only one location your double bond can be. It's between carbon 1 and 2 for both ways, right? This is obviously the only location for 2 carbons, but it could either be here or here. Either way, that's carbon 1 that way, or that's carbon 1 that way. You would number it so that it gets the lowest number, okay? Now remember, when you're trying to figure out how many hydrogens you have on each carbon, every carbon needs 4 bonds. So for example, this middle carbon here already had 1, 2, 3 bonds, so it only needs 1 hydrogen. Okay, now the name of these would just be very simple, ethene and propene. Make sure you're very clearly showing that this is an ENE ending, not an ANE ending. Now, when you get more than 3 carbons, okay, then, like I said, my double bond could be in multiple locations. If it's here, then I would number it 1, 2, 3, 4. And now I have to say where the double bond is. So to do that, I say but-1-ene, because the double bond starts on carbon 1. The isomer for this, so isomer meaning again it has a different name but the same formula. Now I would number it like this, and the name would be but-2-ene. Okay? So that's why when there's only 2 or 3 carbons, you don't need to say where the double bond is because it's always on carbon 1. But here, once I get 4 or more, it could be on carbon 1 or 2. When you get more carbons, 3 and 4, and so on. It can continue to be on different carbons. Okay? We are going to focus on only 1 double bond in our compound. So some examples here. Again, you're finding the longest continuous chain that contains the double bond to be your parent. So none of these have branches yet, but we'll get into branches. So far, they're pretty straightforward. Again, you're numbering it so the double bond gets the lowest possible number. So you're either going to number it from right to left or from left to right. Either way we number it, the double bond is between carbon 3 and 4. Okay, we put the lower number where it starts. So 6 carbons is my parent chain, so that is hex. Then the double bond starts on carbon 3, and then I end in ENE because it has a double bond. So hex 3-ene. Okay, the next one I would want to number in this direction to get the lowest number for the double bond. So that would be pent 2-ene. And the third one, we already looked at this one. This is but-1-ene. Okay, so pretty straightforward when there's no branches. Just make sure you're numbering from left to right or right to left, with whichever way gives the double bond the lowest number. Now, when we get into chains that have branches, the double bond still takes priority in numbering. Okay, so you're going to find the longest carbon chain that contains the double bond. A branch can't be a double bond. Okay, So you need to find the longest chain that contains the double bond, making sure the double bond is numbered the lowest possible number over the branches. Okay? Then, like before, we name the branches first alphabetically, the parent name at the end. So for example, my longest continuous chain here, if this were an alkane, would be to go down. However, that cuts off the double bond. So for alkenes, the double bond has to be part of the parent. Okay, so that has to be my parent. All right, which means this is my branch. There's 2 carbons in that branch. All right, we name the branch first. Again, numbering my parent chain so that my double bond gets the lowest numbers. So on carbon 2, there is an ethyl branch, a 2 long carbon branch, and then the parent is hept. The double bond starts on carbon 1, and then I end in ene. So between every letter and every number, there's a dash. So 2-ethyl, hept-1-ene. There should be no space between the ethyl and the hept. This is one full word. Okay? The next example, my parent is going to bend down this time because that is the longest chain that contains the double bond. So don't forget, you can still bend down if it's part of the longest chain that contains the double bond. I have a methyl, methyl, and methyl, 3 methyl branches, so we're going to combine them to call it trimethyl, right? I'm numbering it again so that my double bond gets the lowest possible number, so I have to number it this way because the double bond takes priority, okay? So I have a methyl on carbon 4, carbon 5, and carbon 6. We put that together to call it trimethyl because there's 3 methyls. My parent is non. The double bond starts on carbon 2, and because it has a double bond, it ends in ene. So 4, 5, 6, trimethyl non-2-ene. Okay? Let's get into cycloalkenes. Now, cycloalkenes, like before, are a ring structure. They have 2 less hydrogens than an alkene because you have to take a hydrogen off of each end carbon to make the end carbons join together in the ring structure. So that is the generic formula for a cycloalkene. Double the hydrogens of carbons minus 2. Now the double bond is always numbered as 1 and 2. So you actually don't have to say where the double bond is because it's always between carbon 1 and 2. Okay? Then you're going to number it. You treat the double bond like a bridge, and you need to cross the bridge first. Go across the double bond first. Then give the branches the lowest number sequence after you cross the double bond. Okay? The name will be cyclo, the prefix, and then ene. Okay? You don't have a number anymore. No number between the prefix and ene because it's always between carbon 1 and 2. You only need numbers for your branches. Okay? So for example, here's my first hydrocarbon. There's no branches. I don't need a number. This would be 1 and 2, or 1 and 2 this way. Either way, it's between carbon 1 and 2. So there are 6 carbons here. So this would be called cyclohexene. Okay? The next one would be called cyclopropene. No numbers needed. Okay? Now, if I were to draw cyclopropene for a second so that we can look at how many hydrogens you have in total, there's a double bond between those carbons and then single bonds. Remember, every carbon needs 4 bonds. So I already have 3. We'll call this carbon 1, carbon 2, and carbon 3. I already have 3 bonds around carbon 1, so it just needs 1 hydrogen. Carbon 2 also just needs 1 hydrogen to make its 4th bond, but carbon 3 needs 2 hydrogens to get its 4 bonds. Okay, so the formula is C3H4. Double would be 6, minus 2 makes it 4. Okay, now when you have branches, like I said, I have to cross the double bond first. So I either go 1, 2, 3, 4, and then my branch is on 4, Or I can go 1, 2, 3, 4. That's the only two ways I can do it. I have to go 1, 2 across the double bond. So obviously the red way is better. It gives my branch a lower number. So we're going to call this 3-ethyl. That's an ethyl branch. It has 2 carbons. And the parent is cyclobutene. Okay, so on carbon 3, there's an ethyl branch of my cyclobutene. The next one, obviously, again, the two different ways to number it. If I number it this way, my branches are on carbon 1 and 3. If I number it the other way, my branches are on 2 and 4. Remember, you're looking at lowest number sequence. Okay, so you're comparing them 1 digit at a time. My 1 comes before 2, so it doesn't matter what the rest of the number is. This is the way you're going to number it. There's a question my students have on a quiz where one way gives them a sequence of 1 and 4. The other way is a sequence of 2 and 3. They very commonly pick this one because the 3 is less than the 4, but that's not what you do. You compare them 1 digit at a time, starting with the first digit. The 1 comes before the 2, so it doesn't matter what the rest of the number is. That's the way you're going to number it. Okay? Lowest number sequence means you're comparing them from the left to the right, the digits, until you get to the lowest one. All right? So, if I'm going to number it the purple way, now I have a, oh, sorry, we're not numbering it the purple way. We're numbering it the red way. Okay? That gives us branch 1, 3. I have an ethyl branch on carbon 3, so it's 3-ethyl. Then I have 2 methyl branches, 1 on carbon 1 and 1 on carbon 3, so that combines them to be a dimethyl. Now notice how the di doesn't change the alphabetical order. It's still the ethyl before the methyl, okay? And the parent is cyclobutene. Let's put up our answers to make sure we're right. Cyclohexene, cyclopropene, 3-ethyl cyclobutene, and 3-ethyl 1,3-dimethyl cyclobutene. Good. Okay? So those are your cycloalkenes. Now let's look at our final one today, alkynes. Notice how they have the same generic formula as the cycloalkenes. So that means they can be an isomer to a cycloalkene. Now what is an alkyne? It has a triple bond. Okay? They are also therefore considered unsaturated. The only time you have a saturated compound is when you have carbon-to-carbon single bonds. If you have carbon-to-carbon double or triple bonds, it is unsaturated. Okay? They can be a continuous chain or a branch chain. They don't commonly exist as ring structures. They're also not very common because they're super reactive. Because of that triple bond, you have 6 electrons in that space. So there's lots of repulsion, making it very reactive. Okay? They are still nonpolar, so they'll be non-soluble in water. They're, like I said, very reactive. The triple bond, again, causes a high force of repulsion. However, they're boiling points. So again, if I'm looking at an alkane, which is C2H6, for example, versus an alkene, which would be C2H4, versus an alkyne now would be C2H2, okay? We have less and less electrons, so we would think it has a lower boiling point. However, there's an exception. There is a linear structure to my alkene, okay? Those are my H's. Because of its linear structure, it has a lot of surface area that other molecules can come right along with its large surface area. They can get really close and interact, and it makes them hard to separate. That's again what your London dispersion forces are. So these actually have a higher London dispersion force than the other 2 types of compounds we've talked about so far. So they actually have the highest boiling point of the 3, okay? So this was my alkane, this was my alkene, This is my alkyne. And if I were to name them, this one would be called ethane. This one would be ethene. And this one is called ethyne. Okay? So the highest boiling point would be the ethyne. Then the ethane. And lastly, the ethene. Okay? All right, let's look at naming them. So as I showed you, you're going to have a Y-N-E ending at the end rather than the other ones we've looked at before. The triple bond, again, needs the lowest number. And again, you need to put a number where the triple bond starts only if you have greater than 3 carbons, okay? Just like the double bond rule, because that's the only place your triple bond can be. When you're naming it, you're thinking to yourself, if I want someone to draw this, how can they figure out where to put a double bond, a triple bond, a branch, and so on? If there's only one location it can be and it gives it the same name, then you don't need to put that information, okay? So this would, again, like I said, be called ethyne. And this would be called propyne. Looking again at your hydrogens, there's only one hydrogen on each of these carbons. One hydrogen here, there's no hydrogens on this middle carbon. It already has all 4 bonds. But this carbon needs 3 hydrogens. So the formula for this would be C3H4. This is C2H2. Okay? Let's get into some parents that have more than 3 carbons. Then we do need to put a number. Oh, I like to use yellow for my parent chain. Okay, so parent chain again is longest continuous chain that contains the triple bond. So these are my longest continuous chains. Then again, I number it so that my triple bond gets the lowest number. So either from left to right or right to left. I think for this one, either way we do it, it's carbon 3 and 4. So the name is hex-3-ine. Okay? The next one, 1, 2, 3, 4, 5, would be pent-2-ine. Okay, so again, very similar to what we do with our double bonds, except we end in -ine, Y-N-E, instead of -ine. When we have branches, again, your parent is the longest carbon chain that contains the triple bond. And then you're numbering it so the triple bond gets the lowest number. The triple bond takes priority in numbering like the double bond would. And you're not going to have a compound to name that has both double and triple at this level, okay? It'll either have 1 double and 1 triple, that's it. Then you name the branches alphabetically, and same as our other rules. So for example, first finding my parent chain, again, longest chain with the triple bond. So I can't bend down because that cuts off the triple bond. This one I can bend down because it's part of the triple bond. Okay? So find your parent chain, identify your branches. That would be a 3 carbon branch. That's a 1 carbon, 1 carbon, 1 carbon branch. Then number it, again giving priority to the triple bond, not the branches. The triple bond takes priority. Okay? So on carbon 3 of this molecule, I have a propyl branch. Remember, that's propyl branch. Okay? And I have 8 carbons, so that's oct. The triple bond is on carbon 1, and it has to end in -ine. So 3 propyl oct 1 -ine. The next one, I need to number it this direction again, so my triple bond gets the lowest number. I have methyl branches on 2, 5, and 6. So this is 2, 5, 6, tri-methyl. We put the methyls together. Oct, 3, -ine. Put up our answers, make sure we're right. 3 propyl oct 1 -ine, 2, 5, 6 trimethyl oct 3 -ine. Perfect. Okay, so that is it for naming your alkynes. There's no cyclic structures we're going to look at for those. Here's just a quick summary again of the different hydrocarbons we've looked at so far. Alkanes, alkenes, alkynes. They are all considered what we call aliphatics. This is different than what we're going to talk about in the next lesson, which looks at something called aromatics. So your compound is either aliphatic or aromatic. If it's not aromatic, it's aliphatic. These ones are all aliphatic. They're all nonpolar, so not soluble in water, and they all have relatively low boiling points because, again, they only have London dispersion forces. However, if you were to order them by boiling point, from the highest to lowest, your alkyne would be the highest, then your alkane, and last would be your alkene. Okay, so just a reminder, an alkane is all single bonds, which would make it saturated. Your alkene is double bond. Your alkyne is a triple bond. Okay, these two are unsaturated. All right, and that's it for alkenes and alkynes. Thank you very much for watching this video.